One of my favorite metaphors for learning to interpret NMR spectra is essentially learning how to drink out of a fire hose. There's so much information there, and it's sometimes overwhelming. How do you start sorting through it? We're in a position now to begin to really get a handle on how we do this. And so I want to walk you through a unknown interpretation from a set of proton, carbon, DEPT 90, and DEPT 135 spectra, using the skills we've been building up so far. On the course website, it told you before viewing this video that you should really have a copy of the spectra and the template for spectral interpretation that we're going to work on to help guide us through this, that you should really have it in front of you. I'm serious about that. This will make a lot more sense if you have it in front of you, preferably even printed out on paper directly in front of you. Now, I know some of you did that and some of you did not. And so if you didn't, go do that. Get that done right now. This will make a lot more sense if you do. For those of you who did print it, enjoy the next few seconds of a video of a baby laughing at a dog. It's amazing what you can find on the internet these days. Now that you have all that stuff in front of you, I want you to take a look at the interpretation template for a moment. Because what I've tried to do here is organize some of the steps that I'd like us to start going through in order to interpret the spectra and produce the structure of this compound. The first thing I asked you to look at is the sample history. Do you know anything about this sample in molecular weight or formula? In this particular example, we do know the compound's formula. We have C10H12O. That allows us to figure out an index of unsaturations. So let's go ahead and get that one calculated now. With the known formula for this compound of C10H12O, it's pretty easy to calculate the index of unsaturations. Turns out to have a value of 5. That's a pretty high number for a relatively small molecule like this. It definitely means you should be on the lookout for signs that this is an aromatic molecule by looking at the chemical shifts of the protons and carbons, and we are certainly going to be doing that shortly. After considering the information we can glean from our knowledge of the sample history, the next part of the template looks at our very first interpretation skill, the number of proton groups and their integrations. So, looking at the proton spectrum of the unknown reveals 5 groups integrating in a ratio of 2 to 3 to 2 to 2 to 3, which does add up to 12. In other words, all of our protons are accounted for. There are several small resonances, little bumps there in the baseline. This is not the world's cleanest sample. There are some contaminants in there. So returning to our template for a moment, we fill in this new information as shown here, and we now move on to the next part, which is the number of groups of carbons in the carbon spectra. Being very systematic with our template, we now look at the carbon spectrum. It is the carbon with the DEPT spectra kind of stacked on it. But for the moment, I want to ignore the DEPT spectra and focus only on the carbon. As I've mentioned a number of times, don't let the fire hose of information overwhelm you. Right now, we're focusing on carbon and the number of carbon groups only. Since you can't process these spectra yourselves, I've included a couple of expansions on the carbon spectra. At regular magnification, it might not be obvious that there are actually 2 very closely spaced peaks above 125 ppm and again around 30 ppm. One of the skills I emphasize when people are analyzing spectra, especially on their own computers, is to look at the peaks closely, zoomed in so that they fill the screen. It is not uncommon especially in carbon spectra, that what appears to be one peak in the normal presentation of a spectrum on paper or on screen is actually two or more when looked at closely. Ignoring the solvent as usual at 77 ppm, the carbon spectrum shows 8 distinct peaks. Note, not 10. Either something is wrong or, hopefully, there is some symmetry in this molecule. So, we fill in the number of carbon groups and move on to our newest interpretation skill, analyzing the DEPT spectra. First up, the DEPT 90. Remember, this shows only CH carbons. All others will either be gone or badly truncated. The DEPT 90 of our unknown here shows 3 CH carbons, all of them clustered together here at around 120 ppm. Moving on to the DEPT 135, the CHs up here in the DEPT 90 are also pointing up, but they are joined by this carbon over here around 30 ppm. Since DEPT 135 spectra show carbons with an odd number of protons attached in a normal presentation, this carbon at 30 ppm must be a methyl group. There are 2 signals inverted in the DEPT 135, must be 2 methylene groups, CH2s. It's interesting to note here that the most upfield resonance in the carbon spectrum is not actually the methyl. It's one of the methylene groups. Kind of curious that it works out that way. It's not common. Finally, there are 2 quaternary carbons indicated. They are present in the regular carbon spectrum but absent in both the DEPT 90 and in the DEPT 135. All total, for the DEPT spectra indicate we have 1 methyl, 2 methylenes, 3 methine, and 2 quaternary carbons. Adding that up, it comes to 8 carbons and 10 hydrogens. Once again, we seem to be missing carbons, and now, from the perspective of the DEPT spectrum, missing some hydrogens as well. It's another indication that this molecule must have some symmetry in it. Now it's on to the chemical shifts, and sometimes it's a good idea to note what isn't there as well as what is in your spectrum. Looking at the proton spectrum, we see 5 total protons in the 7 to 7.5 ppm range. There's nothing further upfield beyond that. This is certainly consistent with an aromatic molecule, a benzene ring, and with the ring having 1 substituent on it, giving the 5 aromatic protons. This would account for the symmetry that we've been hinting at in this molecule, as the 2 ortho and the 2 meta positions of a monosubstituted benzene ring will be equivalent to each other, and also responsible for 4 of the unsaturations that we derived from the formula. Nothing is noted between 5 and 7 ppm, and nothing around 4 ppm at all. No alkene, no protons near an oxygen like you would find in an alcohol, an ester, or an ether. Also, there are no resonances down at 1 or less. We do not seem to have a methyl group at the end of a long chain. There are 7 protons between 2 and 3 ppm, certainly a methyl and the 2 methylenes that we've seen in the DEPT spectra. This is a busy region, 2 to 3 ppm. Protons are not necessarily right next to an oxygen, but they can be near something interesting here. For example, the aromatic ring or even a carbonyl. Looking at the carbon spectra, it confirms certainly the aromatic ring with its 4 carbon resonances representing 6 total carbons in the aromatic region between 120 and 140 ppm. The quaternary carbon here at 140 ppm is certainly the carbon where the substituent connects to the benzene ring. There are 3 upfield peaks, 30 to 45 ppm here, certainly the methyl and the 2 methylenes, and consistent with what we see in the proton spectra. Finally, there is the other quaternary carbon, this one down around 210 ppm. This one, let's face it, is practically screaming ketone at us. We now have more of the template filled in. We've now filled in the chemical shift portion. The next section refers to obvious coupling patterns, which is yet another terrific source of information. We have not covered those yet. Oh, we're going to. Oh, are we going to? But one step at a time. So we're going to skip that one for now. We have enough information now to lay out all the pieces, all the puzzle pieces that we've gleaned from our spectra, and it's time to start trying to put this thing together. The puzzle pieces are a monosubstituted aromatic ring, a methyl group, 2 methylene groups, and a ketone carbonyl. Now, using your knowledge of chemistry, you start fitting these pieces together. For example, if you tried to put a structure like this together, any organic student ought to know this is just absolutely stupid. Frankly, any Gen Chem student ought to probably be able to guess that. Yes, you could put a structure like this one together. It is valid in that it doesn't violate any bonding rules, but it doesn't include all the parts of our molecule either, so something like this has to be thrown out. There really are 3 pretty good structures you could come up with out of these pieces, and here's all 3 of them. All 3 of these structures have the proper chemical formula. All 3 of these structures have the proper number of unsaturations. They are all isomers of each other. But only one structure is the correct structure for this unknown. And it is, for us, the proton chemical shift of the methyl group that really nails it. Because as we've already noted, the methyl group in here at 2 ppm is not likely at the end of a chain. And that rules out these 2 structures and leaves us with just this one, where the methyl group is at 2 ppm near something interesting here, the carbonyl group. And that's how we get the structure of our unknown molecule based upon its NMR spectra. There is even more information, of course, in the NMR spectra, the coupling patterns, all the little split patterns that we see, and that is coming up. So there is even more information out there. But frankly, with the information that we've gone through so far, sample histories, number of groups, integrations, DEPT 90, DEPT 135, you can do an awful lot with those. And so I think those are a good way to begin. Now, admittedly, watching me do this, either in a face-to-face class or online here, is, while dynamic and exciting, I know, it doesn't mean a whole lot if you can't do it yourself. And so, yes, there are a couple of example problems in here, and a couple of these that I'm going to ask you to work on your own. Good luck with those. Feel free to email me questions about it, and let's move on to the next thing.